Nuclear power plants harness tremendous energy through a process called nuclear fission. Imagine splitting heavy atoms like uranium or thorium. That's what happens inside a special chamber called a nuclear reactor. This splitting releases a colossal amount of heat energy. The interesting thing is, the rest of the plant works similarly to conventional power plants that burn coal or gas. In both cases, the heat boils water, creating steam that spins turbines to generate electricity. But here's where nuclear power shines. Splitting just 1 kilogram of uranium produces as much heat energy as burning a staggering 4,500 tons of coal. That significantly reduces the cost and hassle of transporting fuel, a major advantage of these plants. Another benefit is the sheer abundance of uranium deposits worldwide. This means nuclear power plants can potentially provide a stable source of electricity for centuries to come. In fact, right now, they contribute a significant amount, around 10% of the world's total electricity generation. In the power plant, the fission takes place in the reactor, and the middle of the reactor is known as the core that includes uranium fuel, and this can be formed into pellets of ceramic. Every pellet generates 150 gallons of oil energy. The total energy generated from the pellets is stacked in metal fuel rods. A bunch of these rods is known as a fuel assembly, and a reactor core includes several fuel assemblies. During nuclear fission, the heat can be generated within the core of the reactor. This heat can be used to warm the water into steam so that turbine blades can be
Those who
activated.
saw the launch of a
Once the
nuclear
turbine blades
reactor say that
activated,
this is
then they drive the
fantastic.
generators to make electricity. In a power plant, a cooling tower is available to cool the steam into the water, otherwise they use the water from different resources. Finally, the cooled water can be reused to generate steam. Nuclear reactor in a power plant. A nuclear reactor is an essential component like a heat source that includes the fuel and its reaction of nuclear chain, including the waste products of nuclear. The nuclear fuel used in the nuclear reactor is uranium, and its reactions are heat generated in a reactor. Then, this heat can be transferred to the coolant of the reactor to generate heat to all the parts in the power plant. There are different types of nuclear reactors that are used in the manufacturing of plutonium, ships, satellites, and aircraft for research as well as medical purposes. The power plant includes not only includes the reactor, and also includes turbines, generators, cooling towers, a variety of safety systems. The nuclear power plant efficiency can be decided equally to other heat engines because technically the plant is a large heat engine. The sum of electric power generated for every unit of thermal power will provide the plant is thermal efficiency. And because of the thermodynamics second law, there is a higher limit to how efficient these power plants can be. The normal nuclear power plants attain efficiencies approximately 33 to 37%, equivalent to fossil fueled plants. High temperature and more current designs, such as the Generation 4 reactors, could acquire above 45% efficiency. The selection of the site for nuclear power plant can be done by considering the technical requirement. The arrangement and working of a nuclear power plant mainly depend on the characteristics of the site. While designing the plant, the risks from the site must be considered. The plant design has to handle with tremendous natural occurrence and human-induced actions without damaging the operational security of the plant. Each site has to give needed necessities like discarded and decay heat sinks, power supply availability, excellent communications and efficient crisis management, etc. For a power plant, the estimate of the site typically occupies different stages like selection, characterization, pre-operational, and operational. Beyond providing a reliable source of clean energy, nuclear power plants act as engines for local economies. Their construction, operation, and maintenance phases generate a wealth of job opportunities. These positions span a wide range of fields, from skilled engineers to security specialists, offering a chance for many to contribute their expertise. The complex world of nuclear power plants begins with a symphony of engineering minds. Civil, electrical, and mechanical engineers work in concert, laying the groundwork and infrastructure. But the conductor of this orchestra is the nuclear engineer, their expertise guiding the design of the reactor itself and the safety systems that will keep everything in perfect harmony. Once the blueprint is complete, a new melody begins construction. Here, the baton passes to a vast workforce. Laborers, welders, electricians, and heavy equipment operators take center stage, transforming plans into steel and concrete. This construction phase can take years, offering a steady rhythm of employment as the power plant rises, a testament to human ingenuity. Manufacturing steam generators for nuclear power plants is an intricate ballet of precision engineering and rigorous safety protocols. These colossal heat exchangers act as the heart of the reactor system, transferring heat from the intensely radioactive core to a separate loop that ultimately generates electricity. Due to the immense safety implications, every step of the process adheres to strict regulations and undergoes meticulous quality control. The journey begins with colossal steel plates, forged into the designated shapes for the top and bottom heads of the steam generator. These behemoths become the foundation upon which the entire unit is built. Other crucial components, like nozzles and support structures, are also meticulously forged from separate pieces. High-tolerance machining comes next, ensuring each component meets exact dimensional specifications. Even the slightest deviation can compromise the integrity of the final assembly. At the heart of the steam generator lies a forest of thousands of U-shaped tubes. Crafted from special corrosion-resistant alloys, these slender tubes are meticulously bent to maximize heat transfer efficiency. The individual steam generator elements were fusion welded, that is, submerged arc welded, TIG welded, while others were resistance spot welded or cold pressure welded. These welded joints are made of different materials and are of different sizes and shapes. Owing to the variety of materials, the welding procedures were extremely exacting and additional measures were required before, during, and after welding. The most important welded joints and claddings are treated. However, all the welded joints and claddings could not be treated because there are around 60,000 in each steam generator. All 5,428 tubes were joined to the tube sheet at each end by TIG welding, preceded by mechanical rolling in and hydraulic expansion. During the welding process, stresses are set up in the metal. These stresses are due to temperature differences existing in the weld area, and these stresses may be removed or reduced by heat treatment of the metal. One method of heat treatment, called preheating, is to heat the parts before welding in a special oven or furnace. The preheat temperature ranges from 80 degrees Celsius to about 230 degrees Celsius, depending upon the material and thickness. Another method of heat treatment is to heat the parts after the welding has been completed. This method is referred to as post-weld heat treatment or stress relieving. In the case of a boiler drum, for example, after welding of the drum joints, the entire drum can be heated to a specified temperature, 590 degrees Celsius or above, in a special furnace for a definite period of time. Then it is cooled off slowly at a controlled rate until its temperature drops to below 315 degrees Celsius. Imagine a maze-like network where hot reactor coolant on one side transfers its thermal energy to water on the other side, transforming it into steam to drive the turbines. The meticulous welding of these U-tubes to the top and bottom tube sheets is a critical juncture. These tube sheets, acting as both structural support and water flow paths, require immaculate welds to prevent leaks. Stringent welding procedures, overseen by certified professionals, ensure the creation of robust, leak-proof joints that can withstand the immense pressure and temperature within the reactor system. Non-destructive testing, NDT, techniques like X-ray radiography, ultrasonic testing, and eddy current testing come into play at every stage, acting as vigilant eyes to detect any potential imperfections in the welds. Following the meticulous assembly of machined shells, tube sheet assemblies, and other components, the entire structure is welded together to form the complete steam generator pressure vessel. X-ray and ultrasonic testing are then performed with renewed intensity to confirm the integrity of these final welds. Even the slightest imperfection is unacceptable, as even a microscopic crack could have disastrous consequences. However, the process doesn't end there. Once assembled, the steam generator undergoes a rigorous cleaning process to eliminate any contaminants that could affect its performance or, more importantly, compromise safety. A final gauntlet of inspections ensures the finished product meets every stringent regulatory requirement before it's ever shipped to the power plant site. The entire manufacturing process for a single steam generator can take months to complete, a testament to the unwavering commitment to quality and safety. Every step is meticulously documented and reviewed, ensuring these critical components meet the highest standards for reliable and long-term operation within the nuclear power industry. These behemoths are truly the workhorses of the nuclear power plant, silently transferring immense heat energy and enabling the generation of clean electricity.
Алло, хорошо, так вот пусть.
Currently, NPPs equipped with Weaver are characterized with extended surface area of containment shells due to the application of four-loop design configuration and horizontal-type steam generators. It was established that steam generator equipment of horizontal type is characterized by such inherent disadvantages of design, technological, and operational nature as the following. 1. Small height and volume of the vapor space above the evaporation surface, reducing separation capabilities and the capacity of the equipment as a whole. 2. Impossibility of organizing separate single-phase pre-boiling section. Because of the above, horizontal steam generators with dimensions permissible for railroad transportation and, for Weaver 1200, with reactor vessel diameter equal to 5 meters by water transport as well, have exhausted the possibilities for further significant increase of the per-unit electric power. The demonstrated advantages of vertical-type steam generators were as follows. 1. Absence of stagnant zones within the second cooling circuit, and consequently, of hold uses in them. 2. Uniformity of heat absorption efficiency of the heating surface, ensuring, as well, improved conditions for moisture separation. 3. High degree of moisture removal from steam-water mixture due to the combination of moisture-separating elements of chevron and swirl vane types. 4. Increased temperature drop with parameters of generated steam elevated by 0 to 0 MPa.